Hello, I'm Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology. In this video, we will calculate the current in the load resistance, which is the 6 ohm, using Norton's theorem. The steps for the Norton's theorem are again same as I discussed previously. I will go through the steps. Here, the step number 1 is remove the load resistance and short circuit the output terminals. I will name this terminals. This is A and it is B. First step is remove the load resistance and short circuit the output terminals. I will do the same thing. Here we are redrawing the same circuit by removing the load resistance and shorting its output terminals. There is A terminal, this is B terminal. Here this load resistance is removed. This 20 volt with plus minus, 9 ohm, 5 ohm, 4 ohm, 10 volt with plus and minus. And RL is replaced by the short circuit. And our aim is to calculate current in the short circuit. In this current we are interested, I will call it as IN, that is Norton's current. Now here be careful while selecting the method for such cases. Between the terminals A and B we have this short circuit. There is no other element. And whenever any path has zero resistance, in that particular case we cannot use the nodal analysis method, because we are using the nodal analysis method, that is VA minus VB divided by some resistance, and which is 0 in this particular case. That's why its current is coming to be infinite. That's why we should not use the nodal analysis method whenever any branch has or complete branch has zero resistance. Because here we have to use the KVL or direct inspection method, or mesh analysis method, or direct inspection method. I will use the direct inspection method here. This is current I1, here this current is I2, and this common branch current is the Norton's current. You see, if I am preparing the formula for the Norton's current, this IN, which is A to B, then A to B current is I1, that's why its equation will be I1 minus I2. This first we need to calculate the I1 and I2. We can use the mesh analysis also. We can use direct inspection or mesh analysis, both are same. Here in this case, I will use the mesh because I used the direct inspection method many times. This is clockwise, plus and minus. This is again clockwise. This will be the plus, this is minus, this is plus minus, and battery terminals are fixed. If I am using the mesh analysis, we are applying the KVL to the loop number 1. KVL to loop number 1. If we are applying the KVL to the loop number 1, and if we are traveling from this point into the loop in the upward direction, negative to positive, which is plus 20, then minus 9, which is equal to 0, that is minus 20, that is 9I, 1, which is equal to 0. Because there is no common element. That's why 20 is equal to 9 into I1, and here it's current I1, which is equal to 20 divided by 9, which is equal to 20 divided by 9, which is equal to, here it is 20 divided by 9, this value 2.22. This is 2.22 amperes is the current in first loop. If we are applying the KVL to the loop number 2, this is KVL to the loop number 2 for this loop. If we are traveling from this point clockwise direction, positive to negative, which is minus 5 into I2. Then again positive to negative is minus 4 into I2. Then positive to negative, which is minus 10, which is equal to 0. This is the KVL to the loop number 2. If we are separating the terms, then it is minus 9i2, which is equal to 10. That is, I2 is equal to minus 10 divided by 9, which is equal to minus, it is 10 divided by 9. This current is coming to be 1.11 amperes. This is minus 1.11 amperes is the I2. Now here, as I discussed here in this particular portion, Norton's current in this case is the current in the common branch. Current in the common branch, this current. It is IN is equal to, this is IN is equal to, here is the step number 2, this is step number 2. IN is equal to I1 minus I2, this is I1 minus I2, which is equal to, I1 is 2.22 minus of minus 1.11, which is equal to 2.22 plus 1.11, which is 3.33 amperes is the Norton's current. 3.33 is the Norton's current. Now here, if we know the Norton's current, then we can use the step number 3 for the calculation of the Norton's resistance. Step number 3 for the calculation of the Norton's resistance. I will use the step number 3 here. Step number 3. If we are using the step number 3 for that calculation, we are removing the load resistance and removing the sources by its respective interresistance. We should not use this figure for the calculation of the Rn. I repeat many times. Now here, this source will be replaced by the short circuit. 9 ohm resistance will be the same. This 5 ohm resistance will be the same. Here is 4 ohm. This figure will be something like this. Here it is 4 ohm. This is 5 ohm. It is 9 ohm. I am referring this figure. 20 volt source is voltage replaced by its internal resistance, which is 0. Here 0. This 10 volt is replaced by internal resistance, which is 0. RL is replaced and here removed, and here is the A terminal and this will be the B terminal. We should not refer this particular figure for the calculation of the Norton's resistance. Now, for beginners, there is a chance of the confusion which is series or which is parallel. For that purpose, always whenever we have the terminals in between, try to extend the terminals outside. This is A and this is B. Extend the terminals to avoid the confusion. And if we are extending the terminals here, stretch the terminals. If I am stretching the terminals, the figure will be something like this. I am stretching, assuming it is made up of the elastic. Here, this will be the figure. And then we are in a position to find out its value. We are in a position to find out its value. This is of the 9 ohm, 5 ohm and 4 ohm. Stretch. Pick up at the A point and B point and stretch it. If we are stretching, the figure will be something like this. Means here, its final figure will be something like this. Final figure is like this. It is 5, 4 plus 9 and this will be 9. This is A, this is B. And if we are finding its Norton's resistance Rn, which is equal to 9 into 9 divided by 9 plus 9, 81, that is 9 into 9 divided by 9 plus 9. If we are working this calculation, it will be 4.5 ohm. Now we know the two values, Norton's current and Norton's resistance. If I am going here, the Norton's current which we have calculated is 3.3 amperes. Then complicated network will be replaced by the Norton's equivalent network, something like this here. A terminal, this is B terminal, here is the load resistance, which is in this case is the 6 ohm. This is 4.5 ohm, and here this will be the current, which is 3.33. We can find out its load current. Which is equal to total current 3.33 into resistance of the opposite branch 4.5 divided by resistance of both branches, that is 4.5 plus 6. We are able to calculate this load current, which is IL. Now here in this case, if I am doing that calculation, this is 3.33 into 4.5, which is equal to divided by, in bracket, it is 4.5 plus 6 bracket close, which is equal to 1. This will be 1.42. This is 1.42 amperes is the current flowing through the load resistance by using Norton's theorem. Current flowing through the load resistance using Norton's theorem. These are some tricks and techniques can be used while solving the problems based on the Norton's theorem.